So last week we talked about some ideas of fluids, and we talked about fluid systems, density, pressure and forces as far as absolute pressure, gauge pressure, the idea that pressure varies with height. And then we talked about fluids and free body diagrams and some with buoyancy. So we're going to revisit one idea from pressure and forces, which is a Pascal's principle, which lets us use pressure and forces to do useful work. And then we're going to spend the rest of the class working on conservation of energy in fluid flow and conservation of mass and flow rate of fluids. These get a little trickier, so that's why we're spending all of class today just on those two main concepts. There's a lot of variation problems we can do with those. Okay, so last week, one of the things we talked about was pressure and forces and looking at labeling free body diagrams correctly and making sure we have magnitude and direction with our vectors. So like the length of the arrow indicates our magnitude, and then the direction of the point of the arrow is obviously what that is. And then we talked about vectors and forces having magnitude and direction. One of the things of note with ideal fluids and ideal gases, we are going to ignore friction. So I know one of you guys who did submit your assignment labeled friction forces, so we're not labeling those in fluids unless specified. So kind of try to ignore friction and ignore those kinds of things that would happen in real life. And then there was one question, there was a free response question on acceleration. So acceleration is going to be in the direction of the net force. And then there's always force pairs. We talked about that a little bit last week. So question. Yes, unless stated, I assume that the fluid is ideal fluid and frictionless. Good question. Okay, so we talked about this. So this is a review from last week, that weight is going to be in the direction of Earth, and that's mass times gravity. Tension is from a string or a spring, and it's away from the suspended object towards the direction of the string or the spring. Buoyant force is always upward in a fluid, and it's upward force exerted because of the pressure at the bottom of the object being greater than the pressure at the top of the object. And the amount of it is the weight of the displaced water. So whatever the weight of the same equivalent amount of water, that volume of the object will be equal to the buoyant force. And then normal force is only like once it reaches the bottom or supporting surface, then whatever force is exerted on the supporting surface will be also exerted in the opposite direction by the supporting surface on the object. So it'll be always kind of equal and opposite to the force down is the force normal force. And the only exception to that was if there's being an upward force like a string or something once the object is on the bottom. Okay, so one that we didn't get into so much because I wasn't sure we would have time last week is Pascal's principle. And essentially, Pascal's principle says that there's an enclosed fluid that's trapped in a system. And if you apply a change in pressure to one part of that fluid, it's going to be transmitted undiminished to all portions of the fluid and the walls of the container. So we use this every day in hydraulic systems. So most brakes of gasoline-powered cars are hydraulic systems. A lot of big equipment like bulldozers and, trenchers and all those really big equipment have hydraulics, bulldozers and things like that. Hydraulic systems are used in lifts, not necessarily like elevator type lifts. Those are more of a pulley type system, but in a lift that lifts a car up at an auto shop, those are often hydraulic systems. It's kind of like a simple machine. A simple hydraulic system can increase force, but it doesn't do more work on an object than is done in it. And remember that work is force times a distance. So this is kind of a technique we use to move large things, with less input, kind of like a lever, but with water or a fluid. So this is an example. Hydraulic system has two fluid-filled cylinders capped with pistons, connected with a line called a hydraulic line. So if you have a downward force on one piston, if the other piston has a larger area, then the force is also going to be larger. So the force is proportional to the area of the piston. So the force down on A1 with a smaller area is going to multiply that force if we have a larger piston. And again, it works in a similar way to simple machines. Simple machines like a lever, a pulley, you're just changing the direction of the force, not necessarily doing more work than's done, because doing that work is always a force moving something across a distance. So let's look at an example problem. Again, it's proportional. So force 1 is proportional to area 1, and that's proportional to force 2 over area 2. So directly proportional. And remember from last week that pressure is force per unit area. So that's where this pressure is equal to that pressure. Okay, so here's an example. A man pours, and this is from the OpenStax textbook. A man pours remnants of several bottles of wine into a jug after a party. He then inserts a cork with 2-centimeter diameter into the bottle, placing it in direct contact with the wine. That's the important part. It has to be touching the liquid. He is amazed when he pounds the cork into place, and the bottom of the jug, with a 14-centimeter diameter, breaks away. Calculate the extra force exerted against the bottom if he pounded the cork with 120 Newton force. So again, the first thing we need to do is identify all the variables that are in here. So it gives us diameters. Let me get my pen. Okay. Oh, I might need to unplug and replug in my tablet. Hang on, or my thing here. Okay, there we go. Awesome. So let's identify our variables. So we've got the cork has a 2-centimeter diameter, and then the jug or bottle has a 14-centimeter diameter. So they're circular. So the area is going to be pi r squared. So my radius 1 is going to be 1 centimeter, or 2 over 2. Easy math, 1 centimeter. And then my radius 2 will be 14 centimeters over 2, because it gives us diameters and we want radii. So 7 centimeters. And then it says he uses 120 Newton force on the 2-centimeter side. So let's get, so force 1 is going to be 120 newtons, proportional to area 1, which is going to be pi times 1 centimeter squared. And that's going to be proportional to force 2 over area 2, which is going to be pi times 7 centimeters squared. Okay, so we'll just multiply both sides by pi times 7 centimeters squared. I put parentheses around that so I know I have to square it. I always like to rearrange first to get my variable by itself. And then pi will cancel out because it's on the top and the bottom. So we'll have 49 square centimeters times 120 divided by 1 square centimeter. It's a pretty simple one. Pretty simple problems. You probably actually do math on a problem like this. You probably just have to explain how things are proportional. Okay, so I get that the total force 2, is 5,880 newtons. And then it asks for the extra force. So we'll subtract the 120 newtons from that. It said how much extra force was it? Minus 120. And that's 5,760. And let's see, everything is 3 significant figures, so we'll just keep it the way it is. Okay, so pretty straightforward. This type of kind of like looking at the proportionality of it. So if I do have my diameter or my radius, I do need to remember that this is area. That's the main trick of it. So the area is always going to be whatever they give you for the pi times whatever they give you for the diameter over 2 squared. So there will be a squared relationship between diameter and the force, but it'll just be a straight up direct proportion between the force and the area once you do calculate that area. And again, that's area of a circle. If they give you a different shape, like if they're talking about like a different system where it's square or, rectangular, then you would have to use the area of whatever shape they give you. So if you had some kind of rectangular setup, we'd need to do length times width. They aren't going to give you crazy shapes. It's usually going to be a circle or some kind of rectangular prism. Or like a cylinder type deal. Or it'd be pi r squared h if we had to think of a whole cylinder and what it's doing. Okay, here's another example. So let's say the average mass of a car lifted with a hydraulic lift is 1,500 kilograms. Oh, question? Yes, it has to touch the fluid. So let's think about that idea with the jug for a second. And we'll talk about this more next week because we're going to get into gases next week. So let's say we had our jug. So the liquid would have to be like right at where the cork is for that to work. If there is a gap of air, which is what you do when you do a real bottle that you put a cork in, that gap of air is very compressible. So air is compressible, whereas ideal fluids are not. They're non-compressible fluids. So if we put the cork in here and smushed it in, only the air is going to be compressed. It's not going to affect the fluid quite as much. There will be a little bit of increased pressure on the surface of the fluid due to the air having slightly higher pressure, but it's not going to cause something like Pascal's principle to happen. It won't have a direct transfer of the force on this to the fluid. That's an excellent question. Okay, so let's look at this problem again. Okay, so we know we have to lift a car. It's 1,500 kilograms. And then we just want the relative diameters of the pistons if we want to exert a 500 Newton force on one side, on our small piston. And this is irrelevant, actually. This would be relevant if we talked about how much work we would do, which you could figure out, and then you could figure out like the relative heights of them. But this is just asking us for the relative diameters if I want to exert 500 newtons and be able to lift 1,500 kilograms. So first, these aren't the same units. This is a mass, that is a force. So this force can go in for like F2, but this can't go in for F1. So we need to make it a force by doing force as mass times acceleration. In this case, the acceleration is going to be the acceleration of gravity that we have to lift it up against times 10 meters per second squared. So that'll be 15,000 newtons approximately. And we'll have that be F1. And then F2 will be this one. So 15,000 newtons is what we want to lift. And that's over area 1 equals 500 newtons for area 2. And we just want the proportion of our diameters, the relative diameters, like how much bigger does one have to be than the other. So let's just kind of crisscross our proportion here and multiply both sides by A1, divide both sides by F1. And so just divide, so we'll get 30. So our proportion of A1 to A2 is going to have to be 30 times. Now again, think about this is the proportion of our areas. Area 1 needs to be 30 times greater than area 2. But this asks for relative diameters. So to get my relative diameters, I am going to know that this is pi r squared 1 over pi r squared 2. Pi will cancel out. And I can just take the square root of this. And square root of 30 is 5.47. So my ratio R1 to R2 will be 5.47. And notice again, this asks for relative diameters, so I need to double them. And I'm going to round it to a whole number because these are all kind of big whole numbers with 1 or 2 sig figs. So it'd be about 11. So 1 to 11 times bigger. R1. Let's say 11 R1 to 1 R2.
Wait,
Whatever.
why do you have to square root the 30?
Because this is an area. And so the area of the piston is going to be pi r squared.
Okay, so there's two pistons, one big one and one smaller, right?
Yes.
Oh, okay.
Let me just kind of draw. So we've got one that's going to be 11 at whatever x is, and then this one's going to be 1x. So we don't know the units, and we don't know exactly the relatives, how big we want these things, but this one's going to have to be 11 times further across than this one. Pictures always help. Good questions, guys. Any other questions about this particular problem? All righty. So Pascal's.
Oh wait,
Okay.
I have another question.
Yeah.
Why are we doubling 5.47? I thought the ratio between the radiuses is just the same as the ratio between the diameters.
You know what? I think you're right. Yes, because it's a ratio. You're right. So we don't need to double them. Let's get rid of that then. Yeah, because if it's 2 times both, it's still going to be the same ratio. That totally makes sense. So we'll round that to 5.5. So we double one, we double the other one. Excellent. Good mathing. I'm going to cross that off. All right. So that's R1 to R2. Okay. Let me trash this. Go to the next question. Okay, so I've got one for you to try. So we're going to do these in something called Nearpod, so I can see you working it out. So let me copy this link and put it in the chat. So Nearpod's this neat. You probably used it in some of your classes during remote learning or something. But this one lets you, like the instructor, see you doing your work. And then I can kind of look at how you're understanding this question. So if you could open the link I just put in chat, please. Let's just kind of go over it real quick, even though you all ended up getting it correct, which is wonderful. That's excellent. So we've got our two diameters here, and then we've got our force one. So first, like several of you did, some of you put like the calculation in here, and then some of you did it outside of here. I'm just going to put it in here. So 8 newtons is our force one, and then our area one is pi times, whoops, haha. I started to draw the wrong thing. Pi times 3 centimeters over 2 squared. And that's equal to our unknown F1, or sorry, F2, over pi times 0.1 over 2 centimeters squared. And one of the things that might be kind of good practice, some of you guys were doing this, and again, some of you are just kind of, this is a new tool, so might be tricky, but make sure that you show your work as clearly as possible, because as someone who's been an AP grader, if I can find your right answer and your right work, I will give you the points. But if the reader can't find your work because it's just kind of all disorganized, that they might not be able to give you the points. Because a lot of times they'll give you the points if you just have the right work and then even don't end up with the right answer. So if you had this set up correctly, a lot of times they give you the points. Sometimes they need the right answer, but not always. So pi's on both sides. So when I multiply by pi times 0.1 centimeters over 2 squared, that pi is going to be on the top and the bottom, so it can cancel out. I had a chat question real quick. I would suggest putting them in the whole way so they can see what you're doing. Probably not. You probably wouldn't lose points as long as you have your units at the end. But it is good practice because some of these get pretty complicated. So best practice, leave the units in the whole way, because then if you kind of get yourself mixed up, the units will give you a clue. That is a good question, though. You probably won't lose points for it directly, but you might end up making an error. So 0.1 over 2 squared times 8 divided by 1.5 squared. Okay, and I got the same thing all of you guys got for F2. And it's 0.0889, and that would be newtons. And again, this was just 1 sig fig, so most of you went ahead and rounded that to 0.09. Yes.
I accidentally typed in an extra 0, sorry.
Oh no, I didn't type in enough zeros. So you did it right.
Oh, okay. I thought it was wrong there for a second.
Nope, it was me. I didn't type in enough zeros, or didn't write enough
It's fine. It
zeros.
happens to the best of us.
Indeed. Indeed it does. This is the new idea. It is continuity of flow. So this is similar to law of conservation of mass. The continuity equation lets us know how mass, rate of flow in a fluid. So now we're going to start talking about moving fluids. So examples of how we use this is if we're trying to figure out the mass flow rate. So volume flow rate or mass flow rate is when we're going to use this. And the relative equation that we're going to talk more about in a second is the cross-sectional area of a flowing fluid times its velocity is always going to be conserved. So the cross-sectional area times velocity will be inversely proportional. The bigger the area, the slower it goes. The smaller the cross-sectional area, the faster that same fluid would flow. So inversely proportional instead of directly proportional, like the force and area in Pascal's principle. So this is kind of an example picture from the textbook. So the cross-sectional area, whether it's a circle or whatever shape it is going to be like you're using a diameter, again, pi r squared for circles, or if it's a rectangular prism, then it'd be length times width. So the principle is that this same amount of water is going to be continually flowing. If there's suddenly more space for the water, then it'll slow down. If there's suddenly less space for the water, then it'll speed up as far as its linear velocity. So remember, velocity is distance over time. So this distance, this chunk of water, think about it sliding down this tube. The volume rate of flow of this is volume over time. So we have a volume of this flowing over time. And we know that volume is area times the height or distance here. So that's area is times distance over time. Oh, well, distance over time is just velocity. So the area times the velocity of this is going to be conserved. And I can plug into this Q is equal to area times velocity. So if I want the volume rate of flow, that's just going to be area times velocity is the volume that's flowing. And so it's uniform. We're assuming this is uniform. We're assuming that this is also a laminar flow, which I'll show you a picture talking about what that means in a moment. So essentially, the flow rate and the velocity are not the same thing. They're not exactly the same. Flow rate is looking at a volume that's flowing, and velocity is looking at, like, if you had something floating in there, how fast would it be going? So the greater they are proportional, the greater the velocity, the greater the flow rate. But, you know, a little tiny stream and a giant river can have the same velocity of water, but they're not going to have the same volume or mass of water flowing. A big river is going to have much greater mass and a much greater volume of water moving than a small stream, even though they could have the same velocity. So not exactly the same, but very similar concepts. And doing an example probably help you kind of conceptualize this. So we know that the flow rate of blood through the heart is about 5 liters a minute. And so how many cubic meters of blood would the average heart pump if you live 75 years, and we're just assuming, we have to make the assumption that it's pumping the same volume of blood from the time your infancy to adulthood. So we're just doing an average, pretending your heart's the same time your whole life, even though it is not. I just read that and I'm like, wait, you're not going to do 5 liters of blood per minute when you're a toddler, but we're going to ignore that part. Assume that you're your adult size. Okay, so our volume rate of flow is 5 liters per minute, and it wants to know how many cubic meters in 75 years. So this is really just a dimensional analysis problem where we're just converting units. It really isn't a it isn't a volume rate of flow quite, but let's go ahead and look at it. So if we had 5 liters per minute, that's what we're starting with. And we want to end up with cubic meters per lifetime. And our lifetime is 75 years. So cubic meters over 75 years. Okay, so we could do volume measurement or time measurement first. But again, this is really just a metric conversion problem. So I know that 1 liter is 1,000 milliliters. And I know that a milliliter and the cubic centimeter are the same thing. And I know that 100 centimeters is a meter. So if I'm going from linear to cubic, I actually have to cube my units. Okay, so now I have the conversions I need to change the volume. And then I know that in 75 years is one lifetime. And it's certainly not for everybody, but we're pretending for the sake of this problem. And let's say there's 365 days in a year, even though some are longer. That's our average. We could do 0.25 because every 4 years is 300. Let's not be that picky. And then 24 hours in a day. And 16 minutes in an hour. So again, this isn't really a volume flow, rate of flow question. It's more of a metric conversion question. So 1 liter is 1,000 cubic centimeters. And then I have to cube the next conversion, 100 centimeters for 1 meter. And this needs to be cubed. And then that'll give me my, that's not per cubic meter. Well, I want volume on top. Okay. So volume, and I want time on the bottom. So 60 minutes over 1 hour, 24 hours per day, and 365 days per year, and 75 years per life. Okay. So liters cancels liters, cubic centimeters, and then minutes, hours, days, years. Okay, so just a bunch of metric. So 5 times 1,000 divided by 100 cubed times 60 times 24 times 365 times 75. Oops. I made a mistake. I didn't come back down from after the cubing. So un moment. So 100 cubed times 60 times 24 times 365 times 75. Okay, lots. Let me see if I got the same thing I did when I did the problem before. Okay, so I got 19,000. Oh no, 197,100 cubic meters in your life. That's a lot of blood. So that's reasonable though, given 5 liters a minute. Okay, and again, not really a volume rate of flow, but still, it kind of gives you the idea of what this unit is. This is how much volume of liquid is flowing past in any given amount of time. And those volumes could be in any units, just make sure your units match.